Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone. Let us continue our discussion on twinning. In the last class, we started off with the type of twins it forms, and then its origin, and we started describing its characteristics. We would like to continue that, and we are talking about mechanical twinning. So, mechanical twinning differs from slip in the following ways. The twinned portion of a grain is a mirror image of original lattice, whereas the slipped portion of a grain has the same orientation as the original grain. This was quite evident from the pictures we have displayed in the last lecture. Okay, and slip consists of a shear displacement of an entire block of the crystal, whereas the twinning is a uniform shear strain. Okay. So this is one primary difference between a slip and twinning. For a twinning to take place, there is a uniform shear strain is accommodated. That means a cooperative, displacement of atom has to take place. This is very important, right? It is not like few dislocations will glide and you back off systems. It is significantly different from a slippage. The direction of the slip may be either positive or negative, while the direction of shear in twinning is limited to that which produces a twin image. Yes, this is another characteristic. The stress required to produce twinning tends to be higher and less sensitive to temperature than the necessity for the slip. This is another important aspect by which twin is characterized. The stress required to produce a twinning is high. This is a very important point you have to remember. It is still uncertain whether there is a critical resolved shear stress for twinning, although there is some evidence for this hypothesis. So you have to now just look at how we started off with slip. Right? We started off with the slip saying that the primary requirement for the slip to take place is tau CRSS has to have a critical value, that is a characteristic value, and beyond, if the applied stress exceeds that, then the slip starts happening, right? So similarly, if you are considering this as a deformation mechanism, similar situation should arise here, but that is not the case because we are not sure yet. The experimental evidence is not confirmed this is happening. Okay, so it is hypothesized. That is why it is hypothesized. The stress required to propagate twinning is appreciably less than that required to initiate it. Once the twin blocks are created, probably it is easy to move them, and that stress requirement is much less than the stress required to initiate twinning. We will look into these aspects much more closely now. Mechanical twinning usually occurs when the applied stress is high as a result of strain hardening or low temperatures, or in HCP metals when the resolved shear stress on the basal plane is low. So this sentence carries a lot of information. What is that it conveys? Mechanical twinning usually occurs when the applied stress is high as a result of strain hardening or low temperature. That means we looked at some of the work hardening ability or strain hardening ability. When it goes to the very high stage in the strain hardening, for example, we looked at shear stress, shear strain curve for an FCC crystal, where the highest stress, where the material experiences during the stage 3. So that kind of a situation, when whether it is a BCC or FCC, when such kind of situation arises, or alternatively it can be a low temperature, okay, in a normal cubic systems we are considering, or it has to be HCP metals. So why we are referring HCP metals? Because HCP metals are characterized by very less number of slip systems as compared to the cubic systems. This is also another condition. Okay, so that's why the mechanical twinning has it occurs very in a restricted manner. Okay, that is the point I want to emphasize here. Thus, thin lamellar twins called Naumann bands may form in iron loaded rapidly at very low temperatures. So, in a cubic systems, it is very rare. Okay, so unless the load is rapid enough, and also the very low temperatures, this kind of twinning is possibility. I mean, there is a possibility of forming, and typically they are characterized as Naumann bands in a iron crystals and so on. Since slip can occur only on the basal plane in many of these metals, twinning can both contribute to the bulk deformation itself and important, reorient the crystal lattice more favorably for the basal slip. What does this sentence say? You see, we have to remember one point here. We are talking about deformation mechanisms, and we are talking about slip in cubic crystal and twin in the cubic crystal. So when the deformation proceeds in this cubic crystal, still the primary fraction of the deformation will proceed with the slippage only. Only a small fraction will be of twinning. Okay, that you have to remember. But on the other hand, situations where a crystal system is a HCP, or the crystal systems where do not have easy access to the slip systems, are very low temperatures, then the twinning becomes a bulk deformation mechanisms. There is a huge difference. You have to understand this. You have to really remember this. Okay, in a normal cubic materials where the slip systems are available, twinning is only a fraction of the deformed structure, but it becomes a bulk deformation mechanisms or predominant mechanisms only in a restricted conditions or where the HCP metals and so on. So this is very important. And the other point is the only the basal plane in HCP systems reorient the lattice, which is favorable for this twinning. That also we will see now. So this is one illustration of HCP unit cell, where you see that the lattice parameters are not A and C, and this is a 1 0 1 2 twin plane, and this is 1 0 1 1 family of twinning direction. Okay, so these are all the most common twinning plane and direction in HCP metals. And but you have a different situation here in HCP metal. It is very interesting. Whether twinning will result in compression or extension along the C axis is determined by the C by A ratio. Very important. Twinning is going to result in a compression or extension along the C axis, whether it get compressed or elongated. There are two situations that depends upon the C by A ratio. For example, zinc and cadmium with the C by A ratio greater than square root 3 will twin on 1 0 bar 1 2 plane and bar 1 0 1 1 direction when compressed along the C axis. So where is that reference? Yeah. So this image shows that the HCP metals such as zinc and cadmium, which is having C by A ratio greater than square root 3, when it is compressed, then this is the slip system. Okay. Okay. So that means if the C by A ratio is greater than root 3, then it will elongate. The C axis will elongate. That's what it is mean. Okay. When C by A is equal to square root 3, the twinning shear is 0. And lower C by A ratios, the sense of the shear necessary for twinning is reversed. So what does it mean? So this is what these pictures shows that effect. What is that? When the C by A ratio is less than square root 3, for example in beryllium and magnesium, so it is tried to extend along this, or it get compressed along this C axis. The shear deformation associated with twinning causes large local stresses when the twin ends within the crystal. This is again very important because it is a restrictive deformation. It leaves behind large local stresses, okay, especially when the twin ends within the crystal. The formation of a twin is often accompanied by a slip and bending in the surrounding regions of the crystal, and in polycrystalline metals may cause twinning in the neighboring grains as well. So it can induce twinning in the neighboring grains as well. So this is one of the manifestations of this twinning process. So twinning is believed to occur by a dislocation mechanism. Although twinning dislocations have not been identified experimentally. Okay. We have to ask a question here. Why do we believe that it has to occur by a dislocation mechanism? If you recall, when we just looked at a perfect single crystal, okay, we also looked at the theoretical, strength of a perfect crystal. Okay, and if you assume that twinning also takes place without a dislocation or without any assistance of the dislocation, then you have to imagine that how many atoms displacement have to happen in a cooperative manner. Then you imagine that the theoretical strength would be extremely high. Okay, extremely high as compared to, I mean, similar to slip we have just seen. And then we said that only with the help of dislocation motion, the critical resolved shear stress is less in reality as compared to theoretical calculation. So similarly, if you think of a twinning takes place without assistance of dislocation activity, then this theoretical strength would be extremely high. So that is one reason why we believe that twinning also takes place using a dislocation mechanisms. Okay, so this is also a hypothesis, but yeah, we are yet to identify clearly what kind of dislocation assists this process. Okay, let us assume such process would differ from that for slip in two ways. Okay, we are saying that it is happening through dislocation, but what are the primary difference of twinning when it compared to slip process? The Burgers vector of a twinning dislocation does not produce a unit lattice translation. Very, very important. Okay, and this would not bring the lattice back in register. So that means you recall edge dislocation which is moving inside the crystal. When it exits the crystal, it creates a step, and that it's exactly unit lattice translation. Okay. and if it goes in a reverse, normally it will restore the crystal, but in this case it is not going to be the case. Each plane above the twin plane is displaced by a single twin vector, like a slip vector. Here we call it a twin vector. In the mechanisms proposed for twinning in FCC and BCC crystal, the twinning dislocation is one part of a dissociated slip dislocation which can spiral upwards over successive planes when pinned at a screw dislocation normal to the slip plane. Okay, so now what we are trying to understand here is, okay, we are saying that we are hypothesizing that the twinning takes place via dislocation mechanisms. So how it can happen? So how it can happen? What people are believing it is that a perfect dislocation will dissociate into two partials, and then one of the partial, that is a part of the dissociated slip dislocation, that can spiral upwards. So that has to be a screw component, right? Then only it can go up over successive planes when pinned at a screw dislocation normal to the slip plane. So the other dislocation will lie in a slip plane. I mean, the other partial dislocation will lie. The one part will screw will move up to facilitate this twinning. That is what the current understanding goes. The source of this twinning dislocation is most easily visualized in an FCC crystal, for the slip and the twin planes are both 111 planes. So this is one advantage we have. To visualize this hypothesis, we can choose FCC crystal system itself, because in FCC crystal systems, both slip and twin takes place in 111 family of planes. Okay, that is important. So we know what is 111 family of planes, and this is the schematic nicely shows. And you can see this slip dislocation of the type A by 2 1 0 bar 1 dissociate into two partial dislocation as shown here, A by 6 1 2 bar and A by 6 2 bar 1 bar 1. Okay, and this particular A by 6 2 bar 1 partial which remains on the slip plane, and A by 6 1 1 2 bar dissociation which can produce twinning. So this particular type of a partial dislocation which is of screw type will facilitate the twin formation. So this is a twinning vector in FCC. So this is one way of looking at the hypothesis. Okay, dislocation mediated twinning. Okay, we'll look at one more illustration regarding this mechanical twinning mechanism in a BCC lattice by an edge dislocation motion. So this hypothesis can be understood by another illustration. Here, what is that you are seeing? It is these are all a stacking in an untwinned crystal is shown in the schematic, and this is 1 bar 1 1 direction, and then this is the a trace of 1 1 2 in a BCC. In BCC, you have this trace 1 1 2 for twinning, right? So what is shown here is a dislocation, edge dislocation of similar sign. They're all lined up here, and then they all move in a cooperative manner, right? You have to understand this point. See, in a twinning, it is not like a slip. One or two Burgers vectors or one or two edge dislocation will move, but all this edge dislocation has to move in a cooperative manner to accommodate the uniform displacement. So if it moves like this in this direction, in this plane, then it will create this kind of a twin. So this is a twin trace here, and you see that these dislocations try to move in this way, and then it can create a twin like this. So this one way of visualizing how the dislocation is aiding in formation of the twin, but there is no experimental evidence so far. But this helps. Okay, this helps a little bit. When is twinning important? Since twinning and slip can be considered competitive, that mechanism requiring the lowest stress to effect it should be observed. So, see, when is twinning important? Is the question itself relevant only in the case of cubic materials? But in HCP, by default, we can say that it is the twinning will be the bulk deformation mechanisms, right? But given this situation, whichever the mechanisms will carry the lowest stress to effect any whether slip or twin, that will be observed. For FCC metal, the stress required for a flow via slip is almost always less than the twinning stress, and so the twinning is seldom observed in this material. So this is quite obvious, because in FCC materials we have already seen that it is the tau CRSS is there, it is less on the 111 plane. In body-centered cubic, transition metals are more prone to exhibiting twinning. So this is another characteristics. A body-centered cubic transition metals, they are more prone to twinning. And this is because their yield strengths associated with the slip are strongly temperature dependent. Very, very important and fundamental aspects we are touching now. Why BCC metals are, exhibit a yield strength which is highly dependent on temperature. Okay, this is one of the reasons. Thus, with the decreasing temperature, twinning becomes more likely in them. So, in these BCC materials, yielding can proceed with twinning. Okay. Okay, we will talk about this temperature dependent of yield strength as we proceed with the deformation and mechanical testing and so on. Okay, we will concentrate on this aspect much more detail, but this we are just introducing this concept here itself. Slip motion in polycrystals. Okay, so now we looked at the basic mechanisms of plastic deformation called slip and twinning in a single crystals, and then we looked at all possible the details. Okay, now we'll move on to polycrystals, and the word itself says that the polycrystal will have lot more constraints because they have grain boundaries. They are going to strongly pin the deformations. That is one idea. The second important point is the slip planes and direction, which are characterized by the parameters lambda and phi, which is very different from one crystal to the other. Okay, so the tau R, this is a typo here, this is not TR, tau R will vary from one crystal to other, that is critical resolved shear stress will vary from one crystal to other. The crystal with the largest tau R, not TR, yields first. Okay. Other crystals which are less favorably oriented yield later. Okay. So now we'll look at this micrograph. It's very nice illustration here. Polycrystalline material is being subjected to uniaxial tension. That's what it is symbolized here, and this is a scale 300 micron. And what you see here is clearly the grain boundaries. This is a perfect triangle grain, and then you see the grain boundary. You can see the void here, and all the other grain boundaries you can see there is elliptical grains here. And if you look at little more closely inside the grains, you can see that the high dense slip lines are uniformly there. Okay, primary slip lines and then secondary slip lines. These are all signatures of the crystals undergoing multiple slips. Okay. Um, uh, in fact, you can see here all this secondary and primary, secondary and primary, and primary slip bands or multiple slip. Okay, so that is very clear. So now we will try to understand this and what circumstances these things happen and what what happens to the characteristic deformation behavior of each grain in the presence of its surroundings. Okay. Although the basic slip mechanisms are the same in polycrystal and single crystals, their stress strain behavior differs significantly. Okay, very important idea. The deformation response of the grains within the polycrystal are thereby altered in comparison to the response that would be found if each grain were tested as a single crystal. So this is quite obvious, right? Suppose if you imagine that you pull out this each grain and then consider them as a single crystal and then try to deform, they would behave very differently as compared to what it is actually behaving during deformation in the presence of its surroundings. Okay, that is what it means. More specifically, the displacements across the grain boundaries must be matched so as to permit the grains to deform in concert. So what does it mean? Suppose if you are, if you look at this micrograph, this grain is subjected to a tensile force, and then slip lines are approximately, happening in a 45 degree. It's not exactly 45, but just imagine. Okay. But here, if you look at this grain, they are not showing the slip lines similar to the other grains, right? So their slip lines are oriented much different angles. Okay, but somehow the deformation has to proceed because then only the material shape change will happen. With somewhere it has to be accommodated. So for that, the displacement across the grain boundaries must be matched. Okay, see the displacement across this is to be matched, but it is not going to happen so easily. That is a constraint. So that's a first and strong constraint. That's what it is. The very first point is grain boundaries will pin the deformation strongly. That is because of this displacement across grain boundaries are quite difficult to match. In the absence of such cooperative displacements, voids or cracks would appear at the grain boundaries. So this is quite obvious, right? Suppose if the deformation proceeds without the cooperation of all these boundaries, then voids and cracks will form. You can here itself you can see that the boundary which appears here is very different. There, this here itself there is I'm feeling there is a huge step here. So there is a restriction. Each boundary will restrict because of its orientation, right? And if it is not accommodating the strain, it will end up in the cracks and voids. In a physical sense, therefore, neighboring grains restrain the plastic flow of each other, and in doing so, provide a polycrystal with an intrinsically greater resistance to plastic flow than that of a single crystal. Very, very important point. So in a polycrystal, you have intrinsically greater resistance to plastic flow provided by the neighboring grains. Okay, so that's the point we have to remember.